All right, welcome back to CS170. We're picking up on the final week for CS170. So where we left off before, we were talking about the Turing test. Now we're picking up off of that with something called Eliza. Okay, so that was a program that was written over at MIT. And it was one of these things that was like based off of a mainframe. And this is like a typical screen, right? So it wasn't really much in the way of graphics. So you can see kind of did things all kind of like text or character based like this, right? And so what it did was basically you kind of had a conversation with this program called Eliza, right? And so, how did it do that, right? So similar to how we were talking about some of the other examples from the last lecture, it's basically following algorithm, right? So you remember like when you guys were doing your assignments for JavaScript and you had like various like if-else statements, it's almost similar along those lines. Of course, it's a little bit more sophisticated, but you're following a certain set of rules. You're following a certain set of logic. And so that's what Eliza was doing, right? Like I said, in a little bit more sophisticated way, but based on parsing out what you put into the keyboard, the text, the words. So for example, like this, like mother, and this, okay, it will come up with something to further the conversation, right? Usually asking more questions, asking for more information, okay? So it was this kind of like simulating a conversation, right? But obviously this is not gonna be, well, not, I shouldn't say obviously, but this is not a program that would have passed the Turing test, but it's the early days, right? So this is one of the early things that you came up with, the MIT folks came up with. So, so this kind of delves more into the area of artificial intelligence, right? And here's some of the criteria that it looks at, okay? So when you look at like how you deal with everyday life, it's very hard for you to program like all the different possible rules and then have a computer be able to follow it. Okay, simple example would be driving a car, right? So you probably have seen for a number of years the development or the attempt at developing an autonomous vehicle that can drive on its own. Okay, probably the simplest thing would be something like maybe on a fixed track, maybe on a highway or something like that. But once you get into like maybe driving around the city, a very complex environment with people, other cars, animals, whatever, it becomes like way more difficult and challenging, right? And so, the way of trying to anticipate all of the different things you get programmed into a rule just won't work because it's almost infinite, right? And the computer is just, no matter how you do it, it's going to end up hitting a situation that it's not prepared to handle, right? So even right now, you can see, I don't think anyone's close to letting an autonomous vehicle really drive around in like all situations, right? There might be some limited situations where you can do that. And so that kind of tells you where the limit and that where the challenge is, right? But this is what the intelligence is coming from, right? And you're talking about to be intelligent, the computer is not going to go based off of some rules like I gave in the earlier examples, like for Eliza and for these other things up here. It's going to evaluate the situation and then based on some intelligence, figure out a solution and how to maneuver through that situation, right? And you probably hear different things about like, oh, well, if the car is driving along and someone jumps in front of the car, should the should the car try to avoid that person and maybe end up crashing the car and killing the driver, or putting the driver in danger. So there's like a lot of challenging situations where it's very hard to come up with a definite rule as to what to do, right? And the computer with these algorithms will come up with some answers that you're not quite sure how it came up with the answer, right? And that's, again, the crux of some of the challenges with things like autonomous vehicles or artificial intelligence in general. What exactly is artificial intelligence? And then how do you manage that, right? How do you look at it from a moral standpoint, ethical standpoint, and whatnot? So again, this kind of repeats what I was just saying here, right? The actions can't be scripted or pre-programmed, like the rules, basically. And the system would have to understand natural language, right? So this part is actually getting pretty good, although not perfect, right? But like I said, it's getting to the point where I said in the last lecture, you have things like chatbots, things like Google that's able to basically parse natural language and understand that very quickly and come back with a response to that, okay? All right, so one of the early challenges in terms of developing artificial intelligence is the playing chess, and you might have heard about this, right? So in the early days, you would have basically like these ginormous computers, and you basically would grunt your way through, right? If you think about chess, there's like a whole bunch of boards and basically like a lot of paths. It's basically like way more complicated than, let's say, playing checkers, let's put it that way. So here's some of the things that you look at when you're playing chess. Number one, well, you don't have to worry about natural language. So that's good, especially given the days when they started trying to do this. They didn't really have natural language processing yet at that point, okay? And then this is a challenging task. Like I said, it's more challenging than, let's say, playing checkers, right? And then this one is probably a little bit off, right? Playing as early as 1952 that a computer could be a grandmaster in a decade. Took a little while for that to happen, and kind of got a little bit famous with that. So knowing the legal chess moves is one thing, okay? And then they considered this to be sort of like the litmus test, as they're saying here, for AI, okay? So like I was saying before, like each state or each step in the chess game is basically all the different locations on the board with all of the different pieces, right? So you can think of like basically all these different permutations from that, right? So each configuration, all the legal moves, and where they can move and the different weightings of the different pieces and stuff like that. And so you want to try to optimize on the configuration of your chessboard, okay? And so what you do is like, it may not be obvious, but you basically have to look beyond the next step, right? A lot of times you're thinking about not just the next step, but like a few steps ahead and thinking about like based on what you did, what your opponent is going to do in response to that, and kind of like a back and forth, right? And based on those interactions of all the possible moves that you can have, there's basically like a huge amount. It's basically like exponential growth in the number of like chessboards that you would have to evaluate. Okay, so that's why it's particularly challenging, especially given that point in time when they were trying to develop computers to basically do this, right? So they have this idea of a game tree, and you would like evaluate the function to basically optimize which is the right path down the tree that you want, right? So in this way, basically they're saying, well, if the score is positive, it's a good move. If the score is a negative, then it's a bad move, right? And so the higher the score, or basically optimizing a score, the better the move, right? And so the computer has to evaluate those paths of the tree and look ahead, right? And so just so you can see what that tree might look like, this is how you might visualize that tree, okay? So you can picture this, right? Here's the board that you're at with all the different pieces. Obviously, we don't show the pieces here. And then you go down to the next level, like given like however many pieces that you have left on the board and the different things you can do on that, there will be like a whole bunch of these. That's why you see ... here, right? So you have all the different boards for all the different possible moves. And then likewise, based off of that, you have a whole nother series, and you can see how quickly this becomes like ginormous, right? But this is basically how you can visualize or think about it, and how you can see how quickly this becomes like very intense for a computer to store all of these and evaluate all of these. Okay, so you go a few levels down this tree, and you can imagine like it's just going down each of these and just try to come up with a calculation to see what's the biggest positive number it can evaluate. Okay, and so this is what I was just describing, the look ahead. Okay, so it evaluates each move and does the look ahead. Okay, and then like I said, because this tree grows like exponentially, it's huge. And this just kind of makes the point, right? After you look at the first 6 moves, it generates 500 million boards, right? I mean, that's a lot of boards to evaluate, right? And so that's this point here. Okay, so that's kind of like brute force, where you have to go down and look through every single one, right? So we'll kind of get into that a little bit on how they can try to optimize on that. Okay, and this kind of talks about like the opponent and how the opponent, from looking at from the opponent's perspective. Okay, so what's good for you is bad for your opponent, and vice versa, right? So that's why they're talking about the most negative in terms of what you think the opponent will be doing. Okay. Okay. So, so what are the different things that they might have done to optimize here? Okay. You know, so they build up like a database, right? And maybe talking about like some famous sequences or moves, and maybe kind of take some shortcuts there to try to, you know, focus on those as your starting point, as opposed to starting from 0 and just going through brute force, like through all of the possible boards. You kind of give yourself a hint and try to get like almost like a running start and just hit certain types of sequences based on famous strategies, let's say. Okay. And so that's what this is saying here, right? Using a database of openings and end games is giving the computer chess experience. Okay. Now, the other thing, now this is more of like a computer science topic, but just to kind of keep it simple, is this idea of parallel computing. Okay. So as long as like the different boards you're evaluating, they're kind of like separate paths, you can picture that there's no need for you to look at the one path and then go to the next one and then go to the next one. You can actually process all of those like paths in parallel, right? There's no dependency on you completing one task or one path before you can move to the next one. So that's why you have this idea of parallel computing. Okay, so these were a couple of things that they did to try to optimize. If I just went up here and just went through each of these one by one, that's the brute force way of doing it. And very quickly, it becomes like very difficult for even like a supercomputer to look at these, the number of paths to evaluate. And so doing stuff like this helps to make the job easier for the computer to come up with the quote unquote right answer. Okay. Yeah, I should have clicked on this one before. Okay. So the most famous initial attempt at this is the challenge with IBM, which is their Deep Blue computer. and Gary Kasparov, right? So he's like this very famous grandmaster in chess. And they had some competitions, right? So this is back in 1996, which is well past the 1952 initial prediction here, 1952, right? In computer time, it's a long time, right? So in 1996, basically they kicked off these challenges, right? So like I was saying here, what are some of the strategies? Well, one, they had a parallel computer, which was composed of a series of processors, okay, that were doing all these tasks in parallel, okay? Some of them were like just generic ones that, you know, just do addition, subtraction, like the basic stuff. And then chips that were designed specifically to handle tasks optimized for chess. And at that time, the computer didn't do so great. It won one of the games, right? But I guess given some perspective of where it started off from, I guess that was pretty good, right? You win a game, and then you build off of that, right? So that's what Deep Blue did. Okay, and then the improved Deep Blue beat Kasparov the following year. And so what did they do in that following year? They did a couple of different things in terms of course, increasing the horsepower, right? You can always throw more processors at it if you're doing parallel computing. But the other thing was, you know, this point here in terms of like this database of openings and end games. At the time, Kasparov kind of made this argument that basically they were programming the computer specifically to beat him. So basically looking at his his play and basically programming that into the computer. You know, this point here, this database of openings and end games. You know, so that was like one of the complaints from Kasparov. So you can take that for what it's worth, right? And so in terms of horsepower, this is pretty significant here at that time. So at that time, you can picture, this is a pretty big number, 200 million positions per second, okay? You know, at this point, in terms of like horsepower, you know, we've gone, the supercomputers right now have greatly increased. So you can add a couple more zeros to these calculations at this point. And then if you get into quantum computing, you know, that just goes off the chart there. But still, even at that time, that's still pretty impressive. Okay, 200 million positions per second. And so this is like what I was saying, right? You threw more processors at it, right? At the beginning, you had this. I forgot what it actually ended up going to at some point, but it was much more than that. You have like a lot of supercomputers right now that have thousands of like parallel computing chips. Okay, and so because you threw more horsepower at it, then Deep Blue was able to look deeper, right? In terms of that tree that I was talking about. And then this is what I was talking about. Demonstrate whether the computer is intelligent or IBM's team was intelligent. So like I was saying, you know, the IBM team was actually studying Kasparov's play and actually programming things into the database specifically to deal with the way Kasparov played. So again, this is something that you might challenge to say whether this was true computing intelligence, artificial intelligence or not. And then the other limitation here was that Deep Blue was specialized to only play chess. Okay. But still, it was a pretty good accomplishment though. So the next big thing that kind of came along in this space was this AlphaGo. Okay, and this was developed by Google. Okay, and so AlphaGo plays a game called Go, right? And so just like you went from checkers to chess in terms of like the number of permutations that you had to deal with, Go is considered the next level up from that. Okay, so that's why you look at the possible outcomes, you have several orders of magnitude larger than what you have with chess. Okay, and so the difference here is instead of saying, okay, here's all my possible moves, and then trying to optimize and look for like different sequences of moves to build off of or work off of as your running start, like I was saying before, basically Go, AlphaGo basically was teaching itself, right? So it just played the game over and over again, like huge amounts of times, right? And each time it basically built up strategies and optimized off of that, rather than being fed information from people, like in the chess game. Okay, and so the only thing you kind of get from this is basically this whole idea of weighting, right? So in a similar way, you looked at like the positive and negative numbers up here on the chess playing computer. Where do I have it here? Yeah, so all these evaluations here. It's kind of similar thing here with the Go. So you're going through these and like evaluating all these weightings, and then you basically, after you've done it, you kind of pick optimal paths based on these weightings, and you kind of quote unquote prune the tree a bit. Okay, so that was AlphaGo, and then the next thing is Watson. Okay, so Watson is something that kind of added the extra dimension that they took out when they did chess or Go, right? In terms of natural language processing. Okay, so this is what this is saying: chess and Go, right? But then you take it to the whole next level when you're talking about answering a Jeopardy question. Okay, so this is in 2011, right? And then they basically had this IBM Watson computer compete in Jeopardy and win. Okay, and the amount of data that it has to access, or has to store, to access and process, come up with an answer, like it's huge compared to what you had to deal with the board games like chess and Go. Okay, so you have these specialized routines, and basically it's a pretty sophisticated view of evaluating English, right? And again, like all of these different things, that you can have a huge database to access, but the important thing is to be able to pull the information and decide which is the right answer quickly. So you're formulating queries to its database, and then it filters like the results that come back from the database, right? And then it tries to match that up to the question, right? And then ultimately it will just pick one of them and gives that in a spoken English answer. So this is kind of interesting here, right? So basically the database is built from hundreds of millions of unstructured input, right? So these are some examples of the different pieces of data that it pulled in. I'm not sure what they consider to be your standard desktop, but in whatever case, it would take a long time to answer a Jeopardy question on quote unquote a standard computer. Okay. So basically, if you've ever watched the game Jeopardy, you know what the time frame you are looking at to come up with an answer. Okay. Um, so in terms of parallel computing, um, so this is like 2,800 computers. Doesn't really say uh, how many chips or how many cores there are within those computers, but I would imagine it's a lot. And then of course you have terabytes of memory that it's working off of. Okay. Uh, but there's just, you know, some big numbers that talk about like what is involved with doing something like winning at Jeopardy. And so they have this concept. So similar to like you were looking at weightings for like chess and Go, um, similar type of thing for like what they call the lexical answer type or LAT. Okay. Um, so they basically do this analysis based on previous Jeopardy questions. Um, and based off of that, it tries to develop some algorithms or weighting off of those as to essentially what is the answer, right? So similar um, to the chess or the Go, where it's trying to optimize and figure out the best guess at what the right move is. This is how it tries to come up with its weighting for like the right answer to produce for Jeopardy. And this is one of the things that has some more maybe quote unquote practical application. Um, so this kind of goes into, you know, IBM develops corporate software. So there's a number of things in terms of natural language processing that IBM tries to sell, underpinned by some of the work that was done to develop Watson. Okay. So there's just like kind of a screenshot talking about like if you go to the IBM corporate page, you'll see kind of different things here that's tied to the Watson work that they've done. Okay, and I've kind of mentioned chatbots a number of times, but this is the thing right here, the natural language processing layer. Okay, so you have any number of inputs, right? Could be messengers or could be whatever. It goes into this NLP, natural language processing layer, and then goes out to its various sources of information and tries to pull out an answer. Okay, similar to what Watson was doing, right? Now, you know, some people don't do a whole bunch with the chatbots, and some people try to do a lot. Most people, at least if you look at it commercially right now, they don't do a huge amount with chatbots. It's pretty simple. But it is potential to do a lot with it and kind of let it learn by itself, although that kind of has gone pretty badly at some point. So you might see something in old news articles talking about like, you know, some Microsoft chatbots where they basically just left it out there to have any number of people interact with it, and then it tried to build up its database or its intelligence on how it handled conversations in a similar way to AlphaGo did, right? Where it basically taught itself by having a lot of input, right? Playing games, right? In this case, the chatbots that Microsoft put out there was interacting with people via social media and whatnot. That didn't really go too well, right? People kind of fed it some pretty bad stuff, and it ended up going really bad. So there's one of those things where perhaps you want to manage the training of these things and still have to manage it as it evolves. Otherwise, it could go into unexpected directions. Okay. But the concept is still out there in terms of like the quote unquote AI, the intelligence learning based on input. You probably have seen some articles or some videos about computers, AI, basically starting with nothing, just like AlphaGo did, and teaching itself, let's say, how to recognize a cat, right? So how did it do that? It basically looked at gazillion images of cats and started to formulate the different varieties of cats, what a cat might look like. And then that was it. No one programmed the computer to say, this is what a cat looks like. So you'll see more and more of those type of things where basically the computer AI, quote unquote, is just digesting huge amounts of information and drawing or learning from that information, right? Some of the more typical things in medical usage might be like scanning a whole bunch of like x-rays or various scans for cancer or for bone breaks or whatever from a medical standpoint. And eventually it gets a very high degree of accuracy to be able to identify various type of things that normally people might be trying to evaluate. Like a technician may be evaluating, you know, is this like positive for XYZ cancer or something like that. So that's what a lot of these, you know, usually there's supervised learning to have the computer be able to identify various things that normally takes a human. It's a very monotonous and a very long type of thing. They just do it all the time. But these are the typical type of things that computers could be taking over or has already taken over right now. So I mentioned Google, right? So this is one of those things where you have the Google Assistant calling, in this case, looks like a restaurant to make a reservation, okay? So this is just an article talking about that. I think I've mentioned that in the earlier lecture. And this is just talking about like Watson, that as good as it got and it's beaten, you know, pretty tough competitors in Jeopardy, every once in a while I can still get stumped, right? So this is just giving one example where it got stumped. It was talking about the what's the largest airport named after World War II hero and its second airport after a World War II battle, okay? And Watson came up with Toronto when it was Chicago, okay? But it was a relatively minor glitch, I think. But basically, Watson was considered a success, and it's solving a harder problem than Deep Blue. So this is all like sort of the evolution of computer intelligence, right? At least notable that's in the news, right? Obviously, there's a whole bunch of research in this space, and it's continually progressing there. Okay, I think I talked a lot for this lecture, so I'm going to stop it here before I finish up with one more lecture that covers the rest of these slides here that go down to the bottom here for like NP complete prompts and stuff like that. So I'm going to start with Watson, and then I'll continue with the others in another lecture. Okay, thank you.